In this module, we're discussing signal expansions and delta functions. When we're talking about signals, it's useful to make the distinction between discrete time signals or images and continuous valued signals or images. Typically, when we're talking about discrete time, we'll use a notation such as s bracket n, where n is an integer. So for example, this would be a signal, which is indexed with an integer n. And then here is an image which has two indices, s, m, and n. And so we use the integers and the bracket notation. So examples of discrete time images and signals are anything you see on, for example, your computer screen is essentially a discrete time image because we index each voxel or pixel with an integer index. And so, for example, if you have a 2000 by 2000 display, that will have 2000 indices in the horizontal direction and 2000 in the vertical direction. So basically anything we deal with in the digital world we'll want to index and treat as discrete time images or signals. On the other hand, continuous time and space signals are typically what we use to represent objects in the real world. And these are denoted typically with a index of t for time or x for space for a 1D signal or image. And for a 2D image, which we'll be doing a lot in this course, we use x and y to denote the dimensions in 2 dimensions. So for example, this is a 1-dimensional signal here, so index of s of t, so this might be a waveform that we'll use. And here is a 2-dimensional image, s of x, comma y. So when we're representing signals, it's useful for discrete time signals to represent or to introduce what's called the Kronecker delta function. This is a very simple function that's defined as follows. Delta bracket n, close bracket, equals 1 when n equals 0 and 0 otherwise. So for example, here is the Kronecker delta function here. And you can see it's 0 everywhere except for at the origin where it's 1. Now it's also useful to use shifted versions of the Kronecker delta function. In here, in the lower row here, we show delta n minus 2. And so this is a Kronecker delta function that's shifted by 2 to the right. And the way you can tell where the Kronecker delta function is you always look at its argument. So for example, you ask when is the argument n minus 2 equal to 0, and that is when n equals 2, and therefore the Kronecker delta equals 1 when n equals 2. So this is a 1D Kronecker delta function. If we talk about a 2D Kronecker delta function, it's defined as follows. Delta m comma n, close bracket, equals 1 when m is equal to 0 or n equals 0, or 0 otherwise. So here we have the Kronecker delta function. It's 0 everywhere except the origin where it's 1. As with 1D Kronecker delta functions, it's useful to have shifted versions of the Kronecker delta function. So for example, here we have delta m minus 2 comma n. And so basically, the m minus 2 means m minus 2 equals 0 when m equals 2, and therefore the peak of the Kronecker delta is at the coordinates 2 comma 0. Similarly, for delta m comma n minus 2, the peak of that, where that Kronecker delta is equal to 1, is going to be at 0 comma 2, because that's when n minus 2 equals 0. And here we've shifted it both ways, where we have m minus 2 comma n minus 2, and so this Kronecker delta is going to be equal to 1 when the coordinates are 2 comma 2. So, and everywhere else it's equal to 0. So why are Kronecker deltas and the shifted Kronecker deltas useful? Well, it turns out that we can describe any discrete time function, here we have g of n, as a summation of weighted shifted Kronecker delta functions. So each of these is a shifted Kronecker delta function where the shift is by k. And then we also have the amplitude, or the weight, of each of those shifted functions is given by g of k. So this can be done in 1D, so this is the 1D expression, and then this would be the 2D expression, where now you see we have a shift with K and L, so shift in either of two dimensions, and then also for each of those shifts, a weighting function applied. So this is an example here where we have g of n is equal to this function here. It only has 3 non-zero values. And so let's say that this is equal to 1, -1, and 2. Okay? So what we're saying is we can express this as the summation of all these shifted delta functions. So for example, this first point here is represented just by the delta function. This next point here, we use a shifted delta function, but we multiply by -1, so that's this -1 here. And the last point, oh, I guess this is not 2, it's 1.5, is essentially 1.5 times the delta function shifted by 2 here. And so this is a simple example of how you could write this. And so for example, what we'd write is we would say g of n is equal to delta n minus delta of n minus 1 plus 1.5 delta of n minus 2. And that's how we expand that discrete time signal. So we can do the same thing for 2D signals. Here we have an image. It's a 2 by 2 image, which elements A, B, C, and D. And you can see that this could be decomposed into the summation of 4 separate images, where we have this image that has an A here and zeros everywhere else, an image with B here and zeros everywhere else, C here, zeros everywhere else, and D here and everywhere else. And so if you add these 4 images together, you will end up with the image on the left. So how would we write this image decomposition using Kronecker deltas? Well, it's fairly simple. Each of these components here, like this one here, is a 2D Kronecker delta, and then you multiply it by coefficients. So C times this this part here would give me C here and 0 everywhere else. Similarly, this D will multiply this 1 and give me D here. The A will then multiply this, and the B will multiply this. And so what we end up with is a summation of all these components. So for example, let's say that in this example, this is sort of the origin. So this function here is just A times delta M comma N. Here we've shifted the peak by 1. So this is B times delta M let's see, -1 comma n. Here we've shifted in both directions, so this is going to be d times delta m -1 comma n -1. And here we have this component here is c times delta m comma n -1. So it looks like this actually, there's a mistake here. This should be m -1, this should be n, and the d, let's see, the c should be m n -1. Okay, so that's how we write this. And so this is showing that this is this 2D function has shifted Kronecker delta functions, each of them multiplied by the appropriate weight A, B, C, and D, such that we get the resulting image here. Okay. And so we can write this as a double summation where we have basically the sum over all the sort of possible shifts of the delta functions multiplied by their weights.